Hi, everyone. Thank you so much for taking the time to come to my talk. I'm going to be talking about a topic in graph theory, specifically anti-Ramsey multiplicities. Before I get started, I do want to thank the YMC event coordinators for putting all of this together. It really means a lot to me. And also thank you to the Polymath Jr Summer Research Program and my amazing mentors, Dr. Jr and Gabriel. We had a lot of fun doing great research over the summer. So what is a graph in math? Simply, it's a collection of dots connected by lines. We call the dots vertices and the lines edges. So this, for example, is the complete graph of 4 vertices. We say complete graph because completeness is that every vertex is connected to every other vertex. So a K4, means the complete graph of 4 vertices. We typically use the letter K to denote a complete graph. In graph theory, we can do something called an edge coloring, where we color the edges. Like here we have some yellow, some blue, some red. Now, we're going to consider C3 subgraphs. Now, when I mean C3, I mean this right here. It's a triangle, essentially. And a subgraph is like a subset, but for graph theory. So a subgraph is literally where we just take a chunk out of the graph. So that is a C3 subgraph, for example. Notice that every single C3 subgraph, like the one that I've just circled, are rainbows. Now, what I mean by that is that all the edges are colored differently. So here we have a red edge, a blue one, and a yellow one. They're all colored differently. So we call that subgraph a rainbow. Now, our research focused on this. Given a particular type of subgraph, maybe it's a square, a pentagon, a straight line, we want to color an arbitrary Kn with our colors such that we maximize the number of rainbow subgraphs. We want as many of those rainbows as possible. What's interesting is that as n approaches infinity, the maximum number of rainbow subgraphs divided by the total number of subgraphs approaches a constant. That allows us to define 2 types of subgraphs. First, we have the subgraphs in which randomly coloring the edges gives us the maximum number, as n approaches infinity, that is. So for example, let's say problem stats use expected value calculations. We get that 20% of the subgraphs are expected to be rainbows. If the maximum as n approaches infinity is 20%, then we call that our rainbow common. Randomness is the best that we can do. But if we can do better than randomness, then we call that an R rainbow uncommon subgraph. For example, we wanted to look at particular types of subgraphs to see whether or not they were common or uncommon. One such graph is a cycle. So here, for example, I have C3, a cycle of 3 vertices. That's a C4, a cycle of 4 vertices. A C5 is a pentagon, a C6 is a hexagon, and so forth. It's a cycle of n vertices. We conjectured that CK is K rainbow uncommon. So we have a large complete graph coloring it with K colors. The maximum number of CK subgraphs beats randomness as n approaches infinity. We conjecture that we can beat randomness. Specifically, we focused on constructing colorings that beat randomness. One method of construction is the inductive blow-up method. Silva et al. Described this in their paper, which is foundational for this topic of anti-Ramsey multiplicities. Example, let's prove that C4 is 4 rainbow uncommon. So again, a C4 is a square, cycle of 4 vertices, and we are dealing with 4 colors. Step 1, pick a complete graph. We're going to choose a K5 graph, which is the complete graph of 5 vertices. Step 2, we're going to find a coloring of this complete graph that maximizes the number of rainbow subgraphs. We'll use this coloring right here. This has 8 rainbow C4 subgraphs. So for example, A, B, C, D right there has blue, yellow, red, green. That's a rainbow. In total, these are all of the rainbow subgraphs. Step 3, and this is the tricky part, create a recurrence relation that blows up this coloring for a general Kn. So notice that with this picture right here, instead of vertices, I've replaced them with those open circles. And that signifies that in this cell, I've placed 1/5 of the vertices in Kn. Here I've placed 1/5 of the vertices. Here I've placed 1/5 of the vertices, and so forth. So this blue edge means that all of the vertices in here are connected to all the vertices in here with a blue edge. All the vertices in here are connected to all the vertices in here with a red edge. That's what that means. Furthermore, if I were to zoom in to one of those cells, I would actually get a picture of the same thing, only this time we have n divided by 25 in this cell, n divided by 25 in this cell, n divided by 25 in this cell, and so forth. If I were to zoom in into this part, I would get the same picture, only this time with n divided by 1/25 in each cell. So it's kind of like a fractal-like coloring, but of course it differs from a fractal in the sense that this coloring is on a finite number of vertices. This allows us to create this recurrence relation. F of n stands for the maximum number of rainbow subgraphs in a Kn. So f of n is greater than or equal to 5 times f of n divided by 5. What does that mean? Well, there are n divided by 5 vertices in each of these cells. So that means the maximum number of rainbow subgraphs in each cell is f of n divided by 5. There are 5 cells, so that's where we get n of 5 times f of n divided by 5. Plus this 8 times n divided by 5 raised to the 4th. Now, what does that mean? Well, the 8 comes from the fact that this coloring of the K5 that I talked about earlier yields 8 C4 subgraphs. So there are 8 of them. For each of those 8 subgraphs, like let's say this one right here, so the one that goes from here to here to here to here, that one right there, there are 4 vertices. That's where we get the exponent here. There are 4 vertices in a C4 graph. For each of those 4 vertices, there are n divided by 5 options. There are n divided by 5 options in this cell, n divided by 5 options in this cell. So for each of the 8 subgraphs, there are n divided by 5 raised to the 4 ways that we can make that. We need to pick a vertex here, we need to pick a vertex here, and so forth. So that's where we get the 8 times n divided by 5 raised to the 4 part. Now we just need to solve this recurrence relation to get an expression for f of n. If that is better than randomness, then we're good. And in fact, when we do solve this recurrence relation, we do get something than what's expected from randomness. So C4 is for rainbow uncommon. Now, finding the right complete graph and coloring can be very challenging. So in order to prove that C5 is 5 rainbow uncommon, we used this coloring of K8 right here. This has 128 rainbow C5 subgraphs, which is just barely enough needed to beat randomness. We also blew up this coloring of K10 in order to prove that C5 is 5 rainbow uncommon. And what's nice about this one is that we can, this has 544 rainbow C5 subgraphs. The nice thing about this graph is that we can actually take this, and if we replace each vertex with 2 vertices, so for example, take this graph right here, this vertex right here, imagine us splitting it into 2 vertices connected by a 6 color, then we create a K20 graph that has 87,040 rainbow C6 subgraphs. And doing a blow up on that allows us to prove that C6 is 6 rainbow uncommon. So we kind of get a nice 2-for-1 with this graph. Now, in order to help us find these special colorings on the complete graphs that we then blew up, we used a greedy style algorithm. For example, we created a computer program that picked a random coloring, like say this one right here, and it would go through each of the edges and change their colors one by one. If it improved the number of rainbow subgraphs, it kept that color. If not, it moved on to the next one. For example, let's say here we have a K5 graph. We want to make as many C4 subgraphs that are rainbow as possible. So the computer program would start with edge AB, and it would change the color until eventually, oh, it found something that improved the number of rainbows. Then it will move on to the next one, which is AC, and change it until, oh, we got something that improves the number of rainbows. It will go through all the edges and do this, and it would stop when it can't change any of the edges so that it improves the number of rainbows. And this is also a nice way to find a local maximum for the number of rainbow subgraphs. So let's take a break from talking about specific subgraphs and talk about more general results. This is another conjecture that we were focusing on proving, and Silva et al. Again were the ones who put forward this conjecture. So consider a type of subgraph that we know is R rainbow uncommon, like a cycle that we've been discussing. De Silva conjectured that that means that that same subgraph is R+1 rainbow uncommon. In other words, we can beat randomness with R colors. So if we have R+1 colors, we have more colors. That's more ways to color the graph. So we definitely should be able to beat randomness if that's the case. So in order to make headway in proving this conjecture, we wanted to focus on proving this conjecture for specific subgraphs instead of a generalized subgraph. For example, consider K3, which looks like this right here. It's a triangle. We know that K3 is 3 rainbow uncommon. So with 3 colors, we beat randomness. Does that mean that K3 is all rainbow uncommon for all R greater than or equal to 3? And it turns out, yes, that is true. We did prove that. And we did that by using the blow-up method. So let's say we have R colors. We're going to color a KR graph like this. So here, for example, when R is odd and even, there are different ways to color it. So we'll start with odd. For example, here's where R is equal to 7. We can actually color the complete graph in such a way that all triangle subgraphs are rainbows. And the way that we do that is coloring it in such a way that for every vertex, all of the edges connected to it have a different color. So you'll notice right here that the yellows, none of the yellows touch the same vertex. The reds, you'll notice that none of them touch the same vertex. The purples, none of them touch the same vertex. We all keep them parallel to each other. So when we make if we're trying to make a subgraph that is not a rainbow, notice that we're going to need at least 2 edges, 2 different edges. So 2 blues there, which requires 4 vertices. But a K3 graph only has 3 vertices. So that means we have every K3 subgraph being a rainbow. Extending this to even, so a K8, all we need to do when we add our new vertex right here is connect it to the previous vertices with the missing color. So here, notice that that vertex right here has all the colors connected to it except red. So that's the one we use here. The 2, it has all the colors connected to it except blue. So we use that one. And here, same thing, every K3 subgraph is a rainbow. That allows us to create this recurrence relation right here. It's the same as the last one. So we have a KR, so that's where those R's come from. There are 3 vertices in a triangle, and there exist R choose 3 total rainbow subgraphs in KR. Solving this gives us that expression right there for f of n. And now there is an error term, but we can ignore that because it's a lower order of n, so it's a polynomial in n squared. And remember, we're considering this as n approaches infinity. So keep that coefficient of n cubed in the back of your mind. De Silva gives us this expression for what's expected from randomness. Solving that, simplifying it, gives us this expression right here. This is what's expected from randomness. And comparing that coefficient of n cubed with what we've just created, our coefficient beats randomness. We are able to create more rainbow subgraphs than what's expected from randomness. Thus, we've beaten random. K3 is our rainbow uncommon for all r greater than or equal to 3. And we can also extend this result to other graphs. So for example, a K4 graph, which is again the complete graph on 4 vertices, which looks like that. There are 6 edges, so we need at least 6 colors. R is greater than or equal to 6. We want to prove that all of that is rainbow uncommon. And we can use the same coloring as before that we used to prove that K3 is rainbow uncommon for all R greater than or equal to 3. This time, however, the number of rainbow K4s is at least that. So the reasoning behind this is there exist R choose 4 total K4 subgraphs minus the number of subgraphs that are definitely not rainbows. So there are R colors, so we pick a color to be repeated, R ways to do that. There exist R divided by 2 of those colors in the graph. So here there are 8 vertices, so that means there are 4 edges with the color red, 4 with the color yellow, 4 with the color blue, and so forth. And we need to choose 2 of those edges. So for example, choose these 2 blues right here, and we're choosing 2 of those edges because it's a K4 graph with 4 vertices. Those definitely aren't rainbows, so we'll subtract them from the total number to get the ones that are rainbows. And yes, this does undercount the number of rainbows, but that's okay, because we create our recurrence relation with this, solve it, and we still get something that's better than randomness. So future directions, we want to extend this coloring of the complete graphs that maximizes the number of K3 subgraphs. We want to be able to extend that to prove that all complete graphs are rainbow common for all R greater than or equal to the number of edges. Also, another future path, no pun intended, that we want to consider are rainbow paths. So a path is a line, PK is a line with K vertices. So that's a P4, that's a P5. And we want to show that PK is K-1 rainbow common. In other words, we conjecture that we can't beat randomness. We have to prove that for every coloring scheme, that's going to be worse than or equal to what randomness gives us. As a specific case, we tried to prove that P4 is 3 rainbow common, and our justification for that is that Silva proved that stars are rainbow common. So those are what stars look like right there, where you have a central vertex and a bunch of vertex offshoots. So for P4, for example, if we're trying to create a P4 subgraph in a larger graph, all we need to do is pick a middle edge, and then we have all of these other options for the left edge and the right edge. And our motivation for considering it this way is it kind of looks like a star over here on the left and a star over there on the right. So maybe we can use De Silva's result to help us out here. Again, that's just a nice future direction we want to consider. So here's a nice summary of what was known previously. It was known that stars are rainbow common. It was known that the disjoint unions of stars are rainbow common. It was known that K4 minus an edge is 5 rainbow uncommon. It was known that Ka is A choose 2 rainbow uncommon. What we contributed is that C4, C5, and C6 are rainbow uncommon on 4, 5, and 6 colors. We proved that K3, K4, and K6 are rainbow uncommon for all R greater than the number of edges. And for future work, we want to generalize these colorings. For the CM, we want to generalize them so that we can show that all CM are M rainbow uncommon. We want to prove that all KM are R rainbow uncommon for all R. And we want to prove that paths are rainbow common. Thank you so much to the Polymath Jr research team. I have my mentors there and the fantastic students that I have the privilege of working with. Thank you to De Silva et al. For this great foundational paper. And thank you so much for taking the time to watch this. Enjoy the rest of your day.